Hello everybody, welcome to this video, and you probably didn't know it, but you just clicked on a pop quiz if you're one of my students. Yep, that's right, this video is a pop quiz. So make sure you've got this paper in front of you. It's AICE Physics, syllabus code 9702, paper 22 from May-June 2016, question number 4. Pause the video, make sure that you've got that paper in front of you. All right, it's a vocab quiz. We're really just looking at this question 4A, and I'm going to kind of work through 4B here. That's like a review. It deals with base units, and I'm going to work through the rest of the paper too. There's some Doppler Effect stuff here. You'll have a pop quiz on Doppler Effect. Well, I'm not going to tell you when, otherwise it won't be a pop quiz. It says, by reference to the direction of the propagation of energy, state what is meant by a longitudinal wave and by a transverse wave. It's a 2-mark question. I've said it before and I'll say it again, class. Like the Kung Fu master who can use the strength of his or her opponent against themselves, so too can the wise physics student use the strength of the AICE Physics paper against itself. Here's a question from paper 1. It says, a longitudinal wave has vibrations parallel to the direction of transfer of energy by the wave. Now, there's no question there yet. That's just some very helpful information, especially for this question right here. So I'm just going to sort of use this language to answer this question because it very neatly answers the question, right? By reference to the direction of propagation of energy, state what is meant by longitudinal and transverse. A longitudinal wave has vibrations parallel to the direction of transfer of energy by the wave. A longitudinal wave has, you could say vibrations or oscillations. I'm just going to stick with this. Has vibrations parallel to the direction of propagation, the direction of transfer of energy. I'm going to stick with this one. A longitudinal wave has vibrations parallel to the direction of the propagation of energy. So a transverse wave is one that has vibrations perpendicular to the direction of propagation of energy. Did you get that one right? If so, give yourself full credit, 2 marks. A transverse wave has vibrations or oscillations, and we're talking about the particles that constitute the medium through which the wave is propagating. A transverse wave has vibrations perpendicular to the direction of the propagation of energy. And so those two definitions sort of mirror each other. They parallel each other. We just transpose or interchange the word longitudinal and transverse, parallel and perpendicular. That's the key idea. How do the particles of the medium move relative to the direction of propagation of energy? Sometimes they'll say the direction of the wave front. You know, it's like the wave is moving left to right, but the particles are moving up and down. That's a transverse wave. If the wave is moving left to right and the particles are also vibrating or oscillating left to right, that's a longitudinal wave. Thanks, paper 1. The next question, part B here, says the intensity of a sound wave passing through air is given by I, the intensity, which they remind us, they're friendly enough to tell us is the power per unit area, is equal to some constant k that doesn't have any units, v, the speed of sound, rho, the density of the air, f, the frequency of the wave squared, times a, the amplitude of the wave squared. Our job is to show that both sides of the equation have the same SI base units. All right, so base units is a key idea in physics. We sort of make sure that both sides of this equation at least have the same units. In showing that, we don't prove the equation valid, but we can't easily disprove it if the units don't work out. And so let's go through and make sure that this all checks out. I'll start by using the definition that they gave us here. Power per unit area is what intensity is. And so if we just sort of think about it in terms of quantities, we've got intensity, which is power per area. I'm going to write out the word area to not confuse it with, A here for amplitude. Power per area is equal to K, V, rho, frequency squared, amplitude squared. All right, so intensity, which is the same thing as power per area, equal to the rest of this. Now, I'm going to substitute in units for this. The unit of power is watt. The unit of area, the SI units, are meters squared. So a watt is not a base unit, but it is an SI unit, and so we'll sort of leave it like this for now. Now, because K has no units, we're not really concerned with it. V is the speed of sound, so it's a velocity measured in meters per second. Rho is the density of air. So it's important to note that the density of air affects, how much power per area a sound wave is going to sort of be sending through a point. You're typically taught, or you should recall that intensity is proportional to amplitude squared. Right? And in order to turn this proportion into an equation, we need to sort of consider, well, what are the other things that sort of affect that? And, there's a dimensionless constant, the speed of sound, the density of the air, and so on. So this idea is one that you should already sort of be mindful of, and you can see that is sort of embedded within the equation there, that indeed the intensity is going as the amplitude squared. So density here of air, that affects how much power we're going to receive per unit area. How many particles are there sort of per unit volume? And so density, remember, is the mass measured in kilograms per unit volume, meters cubed. And so it should kind of make sense that how many kilograms of air particles we've got per unit volume, that's going to affect how much energy is going to be transmitted per area as that sound wave propagates through the air, right? That's the medium through which sound is passing, sound wave passing through air. So we've got the velocity, we've got the density. Frequency squared is going to be reciprocal seconds squared. The units of frequency are reciprocal seconds, and because it's squared, it shows up squared there in the denominator. And then amplitude is the maximum displacement measured in meters. Don't forget to square that. Some students will just sort of know from memory that the base units of power of a watt are a kilogram meter squared per second cubed. Those are the base units of watts. All right. Other students are not going to have that memorized, but they may indeed have some equations in mind about, power here. And so there's a way to sort of get to this idea if we think about it like power is the rate at which work is done. Work overtime. Good life advice too, right? Work is force times displacement. And remember, from Newton's second law of motion, we can think about force as being mass times acceleration. And so one way to get to the units of power here are to think about it as mass times acceleration times displacement divided by time. And so we have a kilogram meter per second squared times another meter, so meter squared per second squared, and then per time gives us the cubic second. So sort of working with this equation, so remember sort of up here we have quantities, right? P is the quantity power. It's equal to mass times acceleration times displacement divided by time, right? So all of that is power. Here we can see that the meters squared are going to cancel out, and so we get kilogram per second cubed on the left side. And on the right side, these meters squared are going to combine with this meter to give us meters cubed, which will cancel out these meters cubed down here. And so we also get kilogram per second cubed, and so a kilogram per second cubed is equal to a kilogram per second cubed. And so we've shown that they have the same SI base units. The base units of intensity and the product of all of those terms is kilogram per second cubed. Again, an important idea here is we can make shorter work of it the more that we've committed to memory. So just knowing that a watt is a kilogram meter squared per second cubed, but being able to know the equations and substitute in the units is sort of the key idea dealing with base units here. The next part of this question says describe the Doppler effect. That's part C, number 1. It's a 1-mark question. The key idea with the Doppler effect is it's an effect. So a wave travels through space, and if the source of that wave is moving relative to the observer where that wave is being observed, then there's going to be an effect. There's going to be an apparent change in the frequency, and so you need to include sort of language that addresses that. The Doppler effect is a shift in the observed frequency of a wave due to the relative motion of the source of the wave and the observer. So the relative motion is what's important. The observer and the source of the wave are either moving towards each other or away from each other, and that relative motion is going to cause a shift in the observed frequency of the wave. And so the wave is being emitted at a certain frequency, but it will be observed at a different frequency because the source of the wave or the observer is either speeding away from the waves as they're being put out, and so the waves are taking longer and longer to get there, and so it appears that their wavelengths are stretched out, or they're speeding towards each other and it appears that the wavelengths are getting squashed together a little bit more because they're sort of catching up to the waves that they're sending out in front of them. There's a more thorough explanation about the Doppler effect in the slides for this lesson. Part 2 reads, a distant star is moving away from a stationary observer. State the effect of the motion on the light observed from the star. So if the observer and the starlight are moving away from each other, then the effect of the motion on the light observed from the star, it's going to appear that the wavelength of that light is going to be longer, and so the frequency is going to decrease. The wavelength will appear longer. So a longer wavelength from starlight shifts it towards the red end of the spectrum. This is an effect known in astronomy as redshift. Some pioneering work by Edwin Hubble showed that the further away that we measure distant objects, the faster they're receding from us, and he was able to, sort of use the Doppler shift to show that these things were redshifted, that their wavelengths were much more redward than they would be as observed here on Earth. And that showed that they were moving very fast, and the further away that he measured these things, the faster way they were moving, and that kind of led eventually to an idea that, well, the universe is expanding. The wavelength will appear longer. Part D, a car travels at a constant speed towards a stationary observer. The horn of the car sounds at a frequency of 510, and the observer hears a frequency of 550. The speed of sound in air is 340 meters per second. Calculate the speed of the car. Even the wording of this question, as we saw earlier, you can use the strength of the test against itself. An observer hears one frequency, it's emitted another one, there's an apparent shift in that frequency, and so this is a calculation of the Doppler effect. You are indeed provided with a list of formula as you sit for papers 1 and 2. You get this list of equations. The Doppler effect is the one that I've got underlined here, and so it's important to not over-rely on the fact that you're going to have access to this equation. You should be familiar enough with it that you've almost committed it to memory already, but you can check in and just make sure you got the the squareds where they belong, and sort of everything's in the numerator that should be, and so on. Alright, so we'll use that equation here. The frequency that's observed is equal to the frequency of the source times the speed of the wave divided by the speed of the wave. And here we can see that it's speeding towards And when something is speeding towards, we're always going to have to subtract the velocity of the source in the denominator. This is going to make the denominator a little bit lower, and when we divide by a number that's a little bit lower, that's going to make the frequency higher. And so things are more high-pitched, or the frequency is increased as things are speeding towards the observer. And so we need to subtract in the denominator due to this word right here. That means we subtract. If you look at the equation, we can either add or subtract in the denominator, and so we have to use the relative motion. They're either speeding towards or away from each other. If they're speeding towards, it's subtract. If they're speeding away, we add. I'm just going to substitute values into this equation, and then we can sort of do our algebra with that. The numbers aren't so unruly. The frequency that's observed, the observer hears a frequency of 550, and so that's 550 hertz is the observed frequency. The frequency of the source is 510 hertz. The speed v is the speed of sound, and so 340 meters per second. Divided by the velocity of the wave, 340 meters per second, minus the speed of the car. So that's the velocity of the source. And that's the thing that we're solving for here. So we'll leave that together in the denominator. If we multiply both sides by that term, we can get 340 meters per second minus the velocity of the source times 550 hertz equals 510 hertz times 340 meters per second. Divide each side here by 550 hertz. And we get 340 meters per second minus the velocity of the source equal to, we'll turn that into a number at this point, 510 times 340 divided by 550 is equal to this, 315.27. And then if we subtract 340 meters per second, so here we can kind of see that the units hertz have canceled out, and so we do have this as a velocity meters per second. So we're subtracting the same units, which is important. That's one of the key ideas with the base units that we looked at earlier. We can only add or subtract when the units agree there. We couldn't add centimeters per second to meters per second, for example. So I have my 315.27 minus 340 to give me negative 24.73. So if I divided each side by negative 1, about 25 meters per second. Is the speed of the car.